Merry Christmas, math adventurers. We are going to look at the Archimedean spiral, and we're going to start out looking at this in polar geometry. So we have a slightly different form in which we are going to set up our equation and a different way in which we are going to graph this. So instead of an x and a y like we would use on the Cartesian coordinate plane, we are going to use an r, which represents a radius, and a theta, which represents an angle, which we are rotating away from our positive x-axis. So in general, the formula for this is going to look like r equals some number term multiplied by theta. So this is a radius is going to be equal to some number being multiplied by some angle. And this will graph a spiral. And specifically, this type of spiral is called the Archimedean spiral. So let's put some numbers in here and start to see what this looks like. If we want to say that our equation is r equals 3 theta, y3 doesn't have to be 3, could be a variety of numbers. It could be 1 over 360, it could be 2, it could be 3. Many movie franchises happen in trilogies, so why not 3? If we look at this as our equation, then we can start to put numbers in here and look at results. Theta will be our independent variable, r will be our dependent variable. I can set up a table of values here. If I choose 0 for my angle here, then 0 times 3 is 0, so the radius is going to be 0. I can put 30 degrees into here, and if I put 30 degrees into here, I will end up with 90 as my radius. And then I can continue on for some values. When you look at graphing here, we are starting from this axis, and by tradition we rotate in an anti-clockwise direction. So we're rotating this way. So when I look at 30 degrees, I'm starting here as my initial ray for my angle, and I'm going to open this direction until I've opened 30 degrees. This will be my terminal ray. And so if this is 30 degrees, where will my point be that this equation graphs? Well, it's going to be 90 units out. So from the origin, I'm moving 90 units out, wherever that's going to be, and then my point is going to be there. So I had a point at 0, 0, which is down here, and then a plot at 30 degrees, 90 units out. So here, so from here to here, those are my 2 points. And remember, there is a number of angles in between here, so this is not just a line that we're going to connect between here and here. We have intermediate angles in here that we have to account for. What ends up happening is you end up with a curve that comes out here as you look at all the intermediate angles. So that's how we start to get an idea of what this graphs. When we look at this and we restrict it to having the angle run between 0 and 360 degrees, we get something roughly looking like this. So this is saying that we're starting at the angle theta will run between 0, which is what we started with here, and it's going to include all angles for theta up to 360 degrees. So looking at that, we get this type of a spiral. And this may seem interesting, but it's not as interesting as it could be if you allow this angle to exceed 360 degrees. So we're going to go around more than once. And so what happens is this continues to spiral out larger and larger and larger. As we eliminate this restriction on our domain, we can continue to exceed that 360 degrees and continue to go around. And it appears that the distance between these intersection points along the axis here between the curve intersections appear to be the same distance. So that's one of the things that we might explore is, are these distances actually the same? Another question we might ask is, what would happen if we reached in here and pulled this out this direction and added a third dimension to this? Right now we're in 2 dimensions. If we add a third dimension, what might this look like? Another thing to explore is, can we rewrite this in a different representation, be able to graph it in a different way? We are used to graphing x and y points, so is there another way that we could graph this if we take it outside of polar geometry? So these are some topics that we're going to look at. The first one is, if we want to find the distance between these two things, we can use our Euclidean distance formula. This is our Euclidean distance formula. If we know these intersection points, then we can plug those into here and find the distance between these sections. We know right here is 0, 0, because that's the origin. Do we know what this point is here? Well, we know that in the y direction it's 0 because it's intersecting the x-axis. But what is the x value? How far away from x are we when we intersect here? Well, when we intersected here, our angle was 360 degrees. So we started here and we rotated around here and ended here. So that was 1 revolution. So over here, this was 360 degrees in revolution. So if we plug 360 degrees into here, we get that we have to multiply 360 degrees by 3, and that will be our radius. So we have that the radius is 1080 here, so the x value here is 1080. So that's this value here. So we can plug that into here. If we let the origin be our first point and this value over here be our second point, then this is x sub 1, y sub 1, and this is x sub 2, y sub 2. So we can plug those values in here. X sub 2 is going to be 1080, and we're going to subtract 0 from that and square that and add that to our y value. So y sub 2 is over here, so that's 0. Y sub 1 is over here, that's also 0. So we are looking at this. So the distance reduces to 1080. 1080 minus 0 is 1080. We're going to square that. We're going to add 0 to it and then take the square root. So we're going to end up with 1080 as the distance between this point and this point. The next thing that we would want to do is, as we extend the x-axis out this direction, is this next point here. The next point here, so we'll call that point 3. We know again that the y value is going to be 0 because it's an intersection here. We want to know, will this value here be twice this? So we want to know, is the x value here 2,160? All right, so that's the radius. We can check that using our formula. We know this would be the radius, and we want to make sure that this angle here is some multiple of 360. We went around once to get to here. We have to go around twice to get to here. So if we follow this, we went from here, stopped here, that's once, twice. So we've gone around 2 times to get to this point. So let's take a look at that calculation. The radius is going to be 2,160. And that is going to be 3 times some angle. So we want to solve for this angle theta. To get theta isolated, we're just simply going to divide both sides by 3. Dividing 2,160 by 3, we get 720. So the angle to go around to get a distance of 2,160 out here, we're going to have to go around 720 degrees. Now the question is that going around twice? If we take 720 and divide it by 360, we do get 2. 720 divided by 360 is going to be equal to 2, so that's 2 revolutions. That does show that our spacing here is increasing by the same amount. So this is not a formal proof, this is just a demonstration, but we see that as we move out here on the x-axis, we are increasing by the same amount each time. So this is a really interesting curve. It almost looks like concentric circles, but it's a continuous curve that goes out, and it does have this nice spacing effect to it. So that answers one of our questions, is this spacing consistent? And we've given a quick little demonstration that we have some consistent spacing. The next question that I want to tackle is, looking at this polar equation, can I rewrite it in some way that allows us to graph an x and a y value? And to do that, we are going to look at parametric equations. You may not be familiar with parametric equations, but what a parametric equation set does is allow you to write an equation for x and an equation for y, and you have 2 equations that will produce your plotted graph. You do one calculation for your x value, you do a second calculation for your y value. It allows you to have an x and a y, an ordered pair, to graph on the Cartesian coordinate plane, which you are probably used to doing from an Algebra 1 or an Algebra 2 course, where you have one equation, you put in your x as an independent, you get out your y as a dependent, that's your x and y, that's your ordered pair that you would graph. So we are taking a slightly different approach to how we're going to graph this. To change from our polar to our parametric set of equations, we are going to use this set of equations as our conversion factor. For my x value, I'm going to have the radius times cosine of theta. For my y value, I'm going to have r times the sine of theta. What is r? Well, r is our original polar equation here. R is equal to 3 times theta. So we are going to substitute into here our r value, which is 3 theta. So our parametric set will be x is equal to 3 theta cosine of theta, and our y will be 3 theta sine of theta. So this would be our ordered pair. Does this line up with what we had done over here? let's see how that works out. We know that the origin will graph the point 0, 0, and we looked at that. So what happens when we put 0 in for theta over here? Will our x and our y both come out to be 0? So plugging in 0 for this, I have 3 times 0 cosine of 0. That will be 1 point, and then over here I will have 3 times 0 again, and then we will have the sine of 0. This is going to be the ordered pair. When we do this calculation, we want to see that we have 0, 0 turn out here. Is that going to happen? We don't even have to really bother with the calculation of cosine and sine as long as they are defined. So we have to know that 0 is in the domain of both cosine and sine. It is within the domain of cosine and sine. You don't have to take my word for that. You can check it on your calculator if you like. You can look up those values, but those are both defined for the domain. And once we know that they're defined on the domain, we simply have to look at the calculation here. Both of these involved a product of 0. Since we are in a classical algebra, we know that if 0 is a part of the calculation of the product, then the result will be 0. This is the 0 product property. So this one comes out to be 0, 0. You may think this calculation is a little too trivial and you want to see something more robust. You can simply take any of the angles that you know and determine if they came out to the graph that we had prior. And you may find that this is double the calculations that we had before, because for every x we are making a calculation, for every y we make a calculation. But we do have now a way to determine an x and a y, an ordered pair, so that we can graph this on our Cartesian coordinate plane. We knew that 360 degrees graphed this radius. That radius again was our x value, and we know that the y value was 0 because it intersected the x-axis. So this would be another one that you could check on your own. Put 360 degrees in for theta in these 4 locations and see if it gives you x is 1080 and y is 0. The last thing that we want to do is, I asked the question, if we kind of grabbed the Archimedean spiral and we pulled it through into a third dimension, what shape does that give us? So we're going to go on a little field trip for that. This is not a so uncommon Christmas decoration. Notice at the base here we have an X and a Y axis, and this pole acts as a Z axis. The green part here is our Archimedean spiral. Notice they're evenly spaced out here. The end of the curve is over here where you plug it in, and we're going to pull this through the Z direction, and we will get, as we pull this more and more vertical, we get more of this Christmas tree effect here. This particular one's designed to rise a total of 7 feet. So you see, as we continue to raise this pole 7 feet, we get more and more of this kind of a Christmas tree effect. We see there's some inconsistencies here in the physical process, but you get the idea of this Christmas tree effect, and that's what they're doing. It folds into a compact form for production and storage as an Archimedean spiral, and then we move it into the third dimension and we get this Christmas tree-like decoration. Be kind to others in the new year. Keep enjoying your adventures in mathematics and cheerful calculations.